Hello, my name is Rocco Camarere, and this presentation is for the final project in the nano manufacturing online class offered through Stanford University. This presentation will touch on the following. First, you talk about the MOS overview, what are MOS devices and how do they work. In addition, you talk about problems with traditional MOS devices induced from Dennard scaling. Related to the aforementioned topic is an overview of leakage current, and then we also talk about the advent of high K oxides. We also include an overview of 3-5 semiconductors. What exactly are they? These include previous uses of these semiconductors, gains by using these semiconductors, issues by using these semiconductors, and then we'll go into hemp technology a little bit. What does a MOS device do? We start at square one. MOS devices really serve as two main purposes. First, they work as a switch, which transfer data. If you'd like an analogy, this is like Morse code used in the past. It's a series of ones or zeros, or on or off, that will communicate messages, and that's how a computer works. It communicates those in between. And this has to do with the whole idea of a microprocessor, which runs a computer off of this concept. In addition, MOS devices also amplify an electrical signal. I will talk in this presentation more on them working as switches rather than working to amplify electrical signals. There are two types of MOS devices. The first is PMOS, which transfers holes. The second is NMOS, which transfers electrons. And you can join the two to form a CMOS. So what is a MOS structure made of? Whether it's PMOS or CMOS, shown below, NMOS, PMOS, oh, my bad, NMOS or PMOS, CMOS is a combination. They all make up four parts. One is the gate, which is right here, marked G. Second is the drain, here. Third is a source, here. Fourth is a bulk, which is here. Drain is where your charge carriers go. The source is where they come from. The gate controls them moving across. And your bulk is what you start out with at first. Previously, this was silicon. So how does this work? If you look below, you can see in the first picture that there's no charges moving across. This is ideally how this is supposed to work. You start off with 0 volts on your gate, and nothing moves. The small green dots are your electrons. Now, as you apply a voltage to that gate, we're going to use NMOS in this example, you start to create what's called a depletion layer right here. So you have electrons that build up, and that allows your electrons to start flowing. As you continue to apply voltage, you build up what's known as an inversion layer, and you pass what's known as a threshold voltage, which allows these to continually keep moving, the electrons to move more and more. And you can see that in this picture, the electrons are moving from the left to the right, from the source to the drain. In the later part of the last century, scaling of MOS devices for microprocessors was the key to better performance. This is known as Dennard scaling. However, around year 2000, 2004 mentioned in the lectures, major problems started to occur in scaling. First, you have resistivity, which increases because your source and your drain are thinning, as well as your substrate is thinning, but you keep increasing your doping concentrations. If you want a real world perspective of what this looks like, you can imagine bumper cars being your impurities created by your dopants. And as you continue to dope and increase this number, it becomes increasingly difficult for an electron to get where it needs to go due to what's known as problems with your electron mobility. Leakage current also increases dramatically as the MOS device thins, and we'll discuss this in the next slide. Leakage current can take a couple different forms. First, you have subthreshold leakage current. That's where your source is leaking to your drain through your substrate, whether it's this way, through your channel, or this way. Another is gate leakage current, where your channel or your source or your drain is leaking to the gate. Then there's junction leakage current, which is this motion, where you have leaking coming from your substrate to your drain. That can be caused by impurities or a large amount of doping in one of these regions. So what the semiconductor industry did was they started going with higher K oxides with regards to the gate leakage, because as this thinned, this became more prevalent. And so they had to cut this size down in order to the scaling going. And you can see here how the higher K oxides, typically zirconium dioxide, hafnium oxide, those tend to have a higher K than the traditional silicon dioxide, but they have a lower band gap. You now run into the problem of how do you interface traditional silicon with high K oxides. This forms problems with reliability, how long does this thing last, mobility, the cut down on the electron mobility, and charge trapping, or DIT as it's called, density of interface traps. Density of interface traps really affect your device's performance. If you have a lot of interface traps, it's going to really ruin your device. So what I noticed from my research was that with high K oxides, you have roughly with silicon previously, you have roughly 500 to 600 for your electron mobility. However, that's reduced significantly to roughly 200 centimeters squared per volt second when you interface silicon with hafnium oxide. And these results show that. Even with an annealing process, this decreases. And so that's not good for our uses. So we started saying, well, maybe we're hitting a roof with silicon. And this is where 3.5 semiconductors come into play. But what is a 3.5 semiconductor? It's really just a semiconductor made up of elements from column 3 and column 5 of your periodic table. A couple of important elements are gallium arsenide, which is the second most commonly used semiconductor element aside from silicon. Then you also have indium phosphide, which is commonly used for epitaxial growth of indium gallium arsenic, or InGaAs. And then you also have gallium nitride, which has become very popular in the past couple of years due to its higher performance in hemp structures, which we will talk about later. So how have these 3.5 materials been used in the past? Typically, one suggestion is solar cells. In this case, you have 3.5 materials being used quite a bit. One example would be a single cell junction of gallium arsenic reaching roughly 25.8% efficiency back in August of 2008. Today we have more complex structures, such as this one I depict over here, which have found their way onto space exploration, which were used on this robot, which is Spirit, used to scale Mars and to look around. In addition to this, you also have laser technology that you use these, detectors and sensors, thermovoltaics, and then now you have this big wave of LED technology coming with using 3.5 semiconductors. The main reason why this is so important is because these 3.5 semiconductors can be formed into tertiary alloys and other types of alloys that you can control band gap, which is very important in LED technology. So the big question in MOS technology is, how does this make MOS better? Well, first off, you have a very high increase in electron mobility with these materials. As you can see, InGaAs here has over 10 times the electron mobility of silicon, which is incredibly significant. And in NMOS devices, that's extremely important. In addition to that, you also have thermal stability. As I said, you can get different band gaps with these materials, which you could increase the band gap. And by increasing the band gap, you increase the material's ability to handle higher temperatures as well as performing with little noise at low temperatures. All right, so although 3.5 semiconductors have shown a great deal of promise, there are still significant issues. First off, the high expense. The economy of scale of new semiconductors is much different than silicon, which you can buy in bulk. In addition, silicon processes to make silicon wafers and different semiconductor devices is a lot more established and a lot cheaper than using 3.5 materials. In addition, you have issues with the oxide substrate interface, which this is right here, the interfacial layer. You have this high mobility channel that doesn't want to interface well with this high K channel. And then what we use, like I said before, to represent this is the DIT, or density of interface states, or density of interface traps, in fact. Higher these density of interface traps, the worse the semiconductor performs, or the worse that the device performs. And you can see here, this is from a hafnium ingots to hafnium oxide MOS device. And you can see that this is a lot larger than the 10 to the 12th in a typical silicon dioxide device. In addition, you have production complexity. And with 3.5 materials, you have this increasing need for molecular beam epitaxy. And that's a very expensive process, as opposed to silicon, which forms a native oxide of silicon dioxide. These devices do not form that native oxide, or not one that we would want with the properties of silicon dioxide, which have been so good for so many years. So that makes for major problems. And even when you anneal or do post-annealing processes to improve your density of interface traps with, say, ingots to gallium arsenide, you still run into that runs into problems with production complexity. In addition, you have problems with your 3.5 semiconductors in that there's low hole mobility. So let's say that you have a very good electron mobility, but your hole mobility is very low. That cuts down your applications for CMOS applications, and you can see that here with gallium arsenide takes a big hit, whereas silicon is roughly the same, roughly 500 to 600 for electron mobility, but for hole it's roughly 450. Gallium arsenide takes a big dip. And then finally, you have major toxicity problems, that working with things such as arsenic is majorly damaging to humans and so needs to be handled extremely carefully. So now we'll talk a bit about HEMTs, which is an extension of MOS technology. HEMTs are high electron mobility transistors. Typically, they are made with gallium arsenide with ingots as the main channel, or it could be vice versa. But as of late, gallium nitride has started to become a major player due to its better performance than gallium arsenide at higher temperatures and at higher voltages. As you can see here, I've displayed a couple ways to show what a gallium nitride HEMT would look like. You have a gate; it's a bit different structure. It has a T-shaped T gate. You have a source and drain, just like a regular MOSFET. But in this, you have a bit of a different technology, because instead of having of one material, you have different materials placed over each other, normally using molecular beam epitaxy. And they form what are called Schottky barriers. And then that mixed with your channel, and then that produces what's known as a heterojunction, which we see here in our band structure. You can see here there's a conduction band and a valence band. And at this interface here, you'll see that a lot of electrons will come this way and they'll fall into this bin. And that will cause them to become what's known as a 2D electron gas. And this can travel very fast, and it can switch frequencies very quickly. My numbers show that you can get over 600 gigahertz, a frequency of 600 gigahertz by using these devices. Now, these devices seem to produce a lot of things, because they solve a lot. They are very fast. However, they still run into problems with the cost of producing them, the production processes. A lot of these involve significant production processes, and then in addition to that, There are other things such as not knowing what's going on with the interface traps here at these different barriers and fine tuning those. So you can see this will be a major player down the road. And in addition to the regular MOSFET roadmap for semiconductors and 3.5 semiconductors in particular. Thank you for your time.